thank you for the chance to give this talk. I had found out about the CSS initiative. I don't remember how, so just interfacing with who is there in practice and what you guys are talking about is good. I actually very strongly believe in doing whatever, because one thing that's nice about being an applied mathematician is that you don't really ever have to commit to what your topic is, and you can keep working on stuff. And sometimes you can even get away with doing that, which is great. A lot of the slides, especially the ones that are I guess neater and easier to read, I got from my collaborators James Gleason and David Chilai on this. And so when I've started adding colors and various things that make it less readable, then that tends to be my contribution. You can find, but you can download the paper that this is based on from my website. And then I have various online coordinates and so on. I'm mostly focusing on a particular paper, although I'll briefly talk about a precursor that is one that J.P. Onella and Felix Reed-Sohas wrote. And then I'll actually give a little bit of an advertisement that's separate from this paper somewhat before I do the main talk as well. So the other collaborator. So Davida is, he's currently half a postdoc with James Gleason and half working for a company, but he was doing this at the time that he was a postdoc for James Gleason at the University of Limerick. J.P. Onella, who was at Oxford, although now it's sufficiently distant memory that most of you may not know him personally, he's now a biostatistics professor at Harvard. He's getting really into applications of public health, doing a lot of cool stuff. Felix is a local who many of you, of course, do know. All right, so first I'm going to do a shameless plug, and then I'll get back to the main point. Shameless plug is that I have a little booklet with James Gleason called Dynamical Systems on Networks, a tutorial. It's mostly focusing on the models rather than putting in data, but you can have it does have some brief discussions of getting more data in there as well, but it's mostly on the models. There are versions on the archive, so you'll be able to get at least some free version. But then some universities you're able to actually download the final one for free, so you can check it yours. I have not gotten to CD-ROM. So some features. So it's an introduction. It's a friendly introduction. So it'll just kind of tell you some of the landscape and some of what we think about it. There are snarky comments in every chapter. At least one in every chapter. There are Easter eggs in the text. So you can go and you can find them. I mean, paper should be fun to read. I think there's a little bit too much of an emphasis on being staid. And once you're a professor, you can get away with it, which is wonderful. I did some of this stuff before I could get away with it, and it worked anyway. There are discussions of both classical and state-of-the-art topics. So some of the models, some of the classical biological epidemic models, but also some of the newer stuff too. It's short, which is I'm not usually able to do that, but it's short, which is sometimes a good thing. Okay, we're going to be talking about sort of bestsellers today in terms of Facebook applications. So is this book a bestseller? Well, if you go to Amazon, you'll find that a lot more people have published books than I thought. So for example, there are apparently more than 1,500 books in differential equations that you can get on Amazon. I never would have thought that until I found out how poorly we were ranked. Almost 1,000 books in chaos. Okay, anyway, let's go back to the point. But bestsellers are going to show up. So I want to talk about my goals in the talk, and I want to talk a little bit about Facebook data and application installation activity. The important point here about Facebook data, though, this is 2007 Facebook data. So it's not like what it is now at all. This is just sort of the substrate that we're using on what we're doing. This is from the Cambrian era of Facebook, which is 2007. For those of you who've ever used the Facebook 100 data, that's from 2005, which is the pre-Cambrian era of Facebook. And it's going to be, and how Facebook was then is going to be important for how we choose to do this. And I'm pretty sure it wouldn't be true now, but the model that we're trying to develop, the point is not actually Facebook for us. The point is some number of choices with limited attention span. So the hope is that some of the ideas that we think about don't just apply to Facebook 2007, because if they only apply to Facebook 2007, well, why are we doing it? Okay, so hopefully, hopefully we won't have problems with inversion and stuff like that. But so hopefully some of the ideas that are there are things that you might want to think about for some of the modeling you're doing. And we can discuss at the end maybe what types of situations that might be relevant for, but hopefully this will be an idea. And we're going to be thinking about two types of processes, right? So of course other things can occur, but we're going to think about cumulative information, which is going to be a sort of bestseller list. So you might do a type of preferential attachment from a bestseller list. This is a global list that everybody can see. Or you could think about recent information, and that is in the context of a feed, right? You have a news feed, and you might just count bestsellers only up to some amount of time in the past, right? So do you see people downloading apps or installing apps, or do you go to the bestseller list in terms of total number? We'll do some stochastic simulation, and it'll take a while to actually present what the model is. It's going to take quite a bit of time. I'll very briefly talk about a generalization of the model, and on one of the other models out there, if you look at the paper, you will find a somewhat larger list that we think about. Of course, there's obviously more that you can do, and one possible way of interpreting some of the results that we get, and I'm not sure how far I'll get to this today, but one possible way of interpreting it in terms is as a near-critical branching process. So that ends up being buried mostly in the supplementary information of the paper, and then I'll give some conclusions. Okay, so what do we want to do? We want to propose a predictive model of adoption of behavior in an online environment, or can we do that? That's a question that we've kind of asked ourselves. In principle, it could just be choice under limited attention. It doesn't technically have to be online if you once you look at how we actually formulated the model. And one of the things that we try to do, and if you look at the significance statement that we wrote for the publication, we want to talk about the general idea of data-driven modeling of complex systems. But I don't mean big data where I just hit it with something and get an answer out. I actually want equations, partly because I like them, and partly because I think they can tell us a lot of things. But I want to do so in a way that can actually incorporate the data into a model that's still simple. So you could imagine thinking of a very low-dimensional model, but maybe some of the parameters come from fitting the data, right? This is what I call a small data project. I have very ambiguous feelings about big data. So this is a small data project. When we finished this paper, because I had been telling another former OII person, Sandra Gonzalez-Bailon, who many of you know, and also our friend Yamir Moreno, who at least one of you knows, given the institutions that people mentioned. And so Yamir's a physicist, and Sandra is a formerly physics skeptic who now works a lot with physicists, if you actually look at the transition of her opinion over time, at least as characterized by papers she publishes. In any event, I was talking to them, and when we finished our paper and put it on the archive, I sent an email, partly for Yamir's benefit, and said, Yamir, this is our paper on how physicists should really be modeling complex systems. So this paper started its life in a very obnoxious way. And I was making this comment even before we were able to get it into a journal. So you can decide for yourself. And the significance statement in PNAS kind of has that undertone in it, but slightly less obnoxious than the way that I just phrased it. Okay, anyway, those are things that you can decide for yourself. Okay, so Facebook data from the Cambrian era. The precursor paper is something that J.P. Onella and Felix Reed-Sohas did as a data analysis paper. And so if you're interested in the precise details and various things with doing just data analysis, I would recommend to go to that paper. And it was looking at things from that paper that was motivating us. Interestingly, part of the motivation, and this is where the critical branching process ended up coming in, was that James Gleason was looking at a particular plot from there, and I don't have that here with me, finding a 1.5 slope power law, and that is something where you can get certain, as a result of certain types of branching processes. So ironically, the motivation of this paper started with the claim of a power law, but that's something in a prior paper. Anyway, they collected the data. There's 1,200 hours, which is 7.2 weeks, from June to August 2007. This is at a time that when somebody installed an application, it was in your feed. There was no filtering. That's important, right? If there's filtering, I have to worry about a source that was not true then. So you have every feed. Now, we don't have any network structure there. We only actually have the accumulated sizes of all applications at hourly intervals. Okay, well, some of them got launched in the study, some got launched before. We are going to have to worry about that. But once I have 2 consecutive hours, I know exactly how many applications got launched or got installed during that hour. I'm also saying installed because that's what we can measure. I don't know what people are doing. They might install it and never use it. Okay? So there's a leap there because I don't have that other data. So there are quite a few things that are being studied as surrogates because of what we can measure and what people are actually doing, right? So there's quite a bit of a jump there that you really would need more serious data to try to take a look at. Okay, what else do I want to mention? We have no network information, which is good when it comes to privacy. This did not stop the press from trying to, this came out in PNAS 1 week after the pseudo-retraction-ish of this other very infamous PNAS paper with data privacy. And then we came out, and all the press was like, oh, and now, just 1 week after this, these people are doing whatever, ignoring statements in the press release that said there is no personal or network data here at all. They didn't seem to care about that statement. In any event, one consequence of this is that we have to assume, if we're going to do the simplest model possible, that everybody's feed is the same, right? So it's a mean field-like assumption. So now, if you're in a situation, especially with a sampling, that people are seeing different things in their feed, right? That's something that would have to be more complicated than what we're doing. So in a sense, this is a sort of mean field model that you would have to perturb of if you wanted to make it more serious. In order to understand what a non-mean field model does, it is helpful to go to the well-mixed case just to see what happens, right? You know, we do this with epidemic models all the time. Those, though, have the advantage of the mean field models having been studied for many decades. Okay. Another issue that we'll have to think about is whether applications have an inherent fitness. Are some better than another? Or can we use what geneticists would call a neutral model, such that all applications are inherently of the same quality, and it's other features that determine who wins? Okay? So this then becomes a null model, and one of the questions that one should ask for various types of studies that one does, when is it okay to have a neutral model in which you don't care about fitness? How much can you explain? What can you explain? And when do you really have to worry about applications, some being better than another, to explain the dynamics you see? Right? So you have to know what the neutral model does to know what a model with fitness does. But the important question on a given situation is, when is a neutral model fine, and when do you really have to have fitnesses in applications? Okay? So, to give you an idea of just how sophisticated Facebook was at the time, here are the actual top 10. I don't know if this was at the last time point or whatnot, from that data. Number 1, likeness. Number 2, fun wall. Number 3, what's your stripper name? Number 4, my aquarium. Then vampires, Harry Potter magic spells, pirates versus ninjas, booze mail superlatives, and Texas Hold'em poker, which I guess that one did actually allow you to do something. So maybe it's inherently true that what's your stripper name is better than booze mail. I don't know. You know, maybe that's a hypothesis you could have. Okay, and then if you look at the installation data, this is all 1,200 hours. So the total installations will so you have different applications. Some of them get introduced while the data is being collected, so you have to worry about that. So in fact, we're going to end up doing a subtraction so that we calculate applications based on how old they are, and we get rid of a novelty regime rather than based on the original time, right? So we want to compare applications when they're out of the novelty region and for 6 weeks versus things that are heterogeneous. You'll notice that there's an overall increase. I'll show a plot that indicates that, and you have daily cycles. And also, Facebook at the time was, even though it allowed me on US, then it had recently started to, was predominantly focused on a smaller number of time zones than it is now, right? So getting a daily cycle, you're only going to get a strict daily cycle if you actually have the number of hours compressed, right? So you can see that there's a daily cycle. I guess you have to actually measure that that's actually 1 day, but it is. So if you do your trend, it will look like this. So there's a trend line, there's the actual data, and I don't remember what the function psi of t is, but you can put a simple oscillatory function, and it will work reasonably. I mean, this is just to give you a guide as to the rough thing that the data is doing. I don't remember what the functional form is, but we're going to index the application. So I is application I, and we're going to say, all right, well, who have installed application I by hour t? And importantly, if I take ni of t plus 1 minus ni of t, now I know how many people installed it by that point. Before an application is born, nobody installed it. So this ti just says when an application is born. So I have to worry about ti during my window versus not during my window, and a novelty region versus not. And you can sum over this and do a cumulative quantity. Okay, so I'm going to consider cumulative versus recent information. So bestseller lists versus what I see in my feed, subject to going back in time by some amount, right? So more or less, this is going to give me, depending on how you want to count it and how you precisely do it, 2 or 3 parameters. One parameter might be that I have a certain probability or a certain fraction of my users are doing only cumulative, or one person's doing cumulative with that fraction, the complementary fraction doing recent, and then if I'm doing recent, how far back in my time and how am I decaying when I go far back? Okay. So you get so we consider automatic updates on newsfeed when the friends install an app, which was true in 2007 and it's not true now. And Cumulative is the bestseller list. And the user is going to choose a new app with a convex combination of these two, one with a memory window, one with the top. Obviously, there are other things that people could do, and we're only considering what these do to bound it. Although the paper is already rather long anyway, so somebody can just try other things. There are other things to try. There were 921 apps that were launched during the study, so it's launched at some time later. And so in those, we actually get the novelty regime plus the other, and we're only doing predictions, or really retrodictions, about the non-novelty regime, so we end up putting the novelty regime into things directly. This is going to end up being where the small data comes in, so it'll take a few slides to get to this. We're going to shift by the age, because we want to compare apps to each other when they are the same age. Make sure they're out of the novelty regime. So that's what this is doing. And we can only actually accurately compute the age if something is launched after they started collecting data. Okay, so let's see, what else? Oh yeah, so two examples. So in terms of a novelty regime, it looks like this might be exponential and it looks like it might be linear, right? And if you do Texas Hold'em poker, you see the same thing, and you actually see some of those things in general. Remember, this is only installation. You could, if you install it once and you never use it, this is counted just the same as if you install it. And you're playing Pirates versus Ninjas every hour. Those count the same. So that's obviously an approximation. So the mean scaled growth rate would then be, say, the slope after you get out of this novelty regime. Of course, it's an issue of how long the novelty regime lasts. You'll notice it doesn't have to be uniform. Okay, so we want to represent apps with very different popularities. Younger apps grow faster, and then there's a sort of a quasi-steady state. In principle, if you do a statistical model, you probably could model as a statistical steady state. We did not do that. And then you have this novelty regime, and you have, so the number of hourly installations is going down, although there's still the day-night cycle. And then you have the quasi-steady state, in a sense, is supposed to say that this trend is almost constant, right? And then, as I said, you could probably formalize it, or you can formalize it statistically. What we do is that we're going to actually impose the novelty regime data into the model directly. So you'll see this later, so that we can only make predictions outside. And the reason that we're going to end up getting in our calculations the day-night cycles after the novelty regime is because we impose the day-night cycles from the novelty regime. Otherwise, the model would not be able to have the oscillations. Okay, so this is how the data is inserted. And it'll end up being, I think the best fit ends up being about 1 week out of the 7 weeks being inserted. So 1 out of 7 is more than I would like to, but there's something there about how much should be inserted before what you do there. But if you had data coming in streaming, in principle, I could stream my data and say, I've done this, and now everything that comes in hence, I will not put in, I will actually predict, right? We didn't try that for this, but one could imagine an experiment with Twitter or whatnot, which one does it. And some of the work that has followed on from this, and this is work that I'm not on, but Yamir Moreno and James Gleason and others have been doing it, has exactly been going in that direction, becoming even more mechanistic and trying it like on the 15M data and so on. Okay, another thing you could do is ask, is there a difference, if you take all these launched in study, applications, is there a difference from the ones who launched earlier, which are in blue, and the one who launched late? And at least with a cumulative distribution, it looks they're relatively similar. So we're not worrying so much about Facebook having changed during the era in which we were studying it in those 2 months. So this is just, that's kind of meant what that plot is for. And they both together, at least qualitatively, look similar to the other. This one's larger, the black one's larger just because there's more applications in it. Okay, so now let me give you a cartoon of the cumulative versus recent rule, and then eventually we'll get up to formulas. So I is application I, and so this is going to be the probability of a user installing I. And remember, I can either think of gamma as the fraction of time I do one rule versus the other, or I can think of gamma as the fraction of users who always do one rule versus the other. The first is, of course, more realistic in terms of how people might behave, although still a toy. And the second sometimes makes it easier to think about where the mathematics goes. Okay? All right, so we imagine application 1 versus application 2. If we're talking about the recent activity rule, then we're saying, all right, I have time going down here. This H is going to be the window that I'm just actually imposing the data. But imagine my window of length H, and I ask, okay, who has been installed more often, perhaps with a decay rate, in the window of length H, right? So this is me going into my feed and scrolling down, and eventually I get bored. And there is evidence with some social media that people do this. So the ones that I know about, and maybe there's more, there's one that people studied Google, I don't remember who did this, but they basically said, okay, if you're on the first page, we're good. As soon as you go to the second page, not so much. But that is a discrete situation. This is a continuous scrolling, and Christina Lerman from ISI over at USC has done work certainly on Dig and on Twitter, basically saying there's a certain decay rate as far as how far you go. So I don't remember the exact details. In fact, we tried several different functional forms for this decay rate, and qualitatively, at least in this example, they all give the same result. We chose them for convenience, but the point is there is evidence for this sort of decay rate and a window that you should not go back to infinity, right? Empirical evidence for that. I don't know what it would be on Facebook per se, but the important parts of this project are not what we can say about Facebook, but rather what can we say about choices in an online environment subject to our own, limitations. Okay, so how much of their feed do they remember? So you've got the recent rule, which you do with probability 1 minus gamma, and then with probability gamma, you do the cumulative rule, which is going to be a sort of preferential attachment, the simplest type of which is a linear preferential attachment. So if you then just do gamma equals 1, that would be exact preferential attachment of whichever functional form we chose to use. And that's just saying I look at the top list, I look at the numbers we did the numbers rather than just the rankings. There was also a ranking model by Radkevich that we compared with, but you'll have to look at the paper for that. And that just says, okay, preferential attachment. So a lot of models that are out there tend to do preferential attachment or a variant thereof, right? And we're arguing that for a lot of situations, you should not only consider preferential attachment, but there are other rather fundamentally different types of mechanisms that could also be in play. And so this one's just a trade-off between two different ones, very far from exhaustive, but just to illustrate a point. And then a user chooses application I with probability pi, and then I still have to give you functional forms. Yeah?
Have you thought of a preferential attachment with the fitness function, which is time dependent?
You could do that. We did not, I believe we did not try that in this particular case. By the way, we ended up finding out that for this application, at least according to our calculations, not having fitness works better for this one. But I think one of the most interesting questions is, when does fitness matter, when does it not matter, right? Because surely some of the dynamics we see don't need fitness. And so it just should be different applications. To me, that's one of the more important questions to be considering, because we want to know when the quality actually makes a difference to what you see and when you shouldn't care, right? Like that's really fundamental. Okay, so I still have to give you functional forms, which I haven't done yet, but we're gradually getting to that. Okay, so as I said, if you're doing the recent rule, you need to have a history window parameter. So we end up at some point doing a very expensive, computationally expensive fitting to find out what is our best one that we see. And up through this H, this blue thing over here, and so the data is the data. We've showed you that plot already. This H says I'm going to just take the data, and for this H, that is the data. And remember that this H refers to an application having existed for H units, okay? Because and it's going to end up covering the novelty regime, so anything that we predict, although as I said, really retrodict, is always going to be outside of the novelty regime in this quasi-steady state. Okay, so this is imposed, so that will automatically be correct. And then we ask, okay, now we have these rules, and what happens? All right, so I'm going to reiterate this. We've got our convex combination of the recent and cumulative rule with formulas I have not told you yet. Cumulative rule is a form of preferential attachment. We end up doing linear preferential attachment, and the recent rule is looking at my feed. There'll be some decay rate that will go a certain amount. Okay, cumulative rule. They look at the top list. They look at the bestseller list. They don't go back down to the 3 million and something book, right, unless they really are patient. Listed by accumulated size, and we're actually using the size, not just the ranking. So you can also argue whether you should do the rank, we actually do the rank order and not worry about the numbers. I would think that for most applications, probably the rank order is more important than the numbers themselves, but anyway. Then this is linear preferential attachment. The K is just a normalization, and so at t minus 1, there are a total of ni installations of application I, and therefore I'm going, this is the that proportion of those is going to give me what I would do in this case. Okay, and then I could also do, or alternatively do the recent rule. I look at what's on my feed. Remember, I have no network information, so we're assuming everyone has the same feed, and that Facebook therefore is well connected enough, or at least homogeneous enough, so that that's reasonable. I don't think that Facebook in 2007 was, but at least for this data set, it seemed to not matter. So essentially, the mean field seemed to do very well. But this is one to worry about because that is an assumption. And we did this probability of installation. W is a memory function. I'm going to have to give you a formula for that. But if I were looking at somebody's Twitter activity and I measured empirically what their decay rate was, W is where I put that in. Right? So W is where you can either take a formula or you can put it directly in from data. Right? We did it for a formula here. I've got a convolution, a discrete convolution. So W gives weight to t hours from the past. We have, so time collection is once an hour in our case. So this is why we're doing this in a discrete way. If you use certain type of models, you have to do it in a continuous way. The L is just, again, normalization. And you can express this if you want as random copying with memory rules. And so Bentley has done quite a bit of work on those sorts of rules. And work by Bentley was very much motivational in terms of things that we had seen before we did this. Okay, so we do some stochastic simulations. So we're copying from the history window, and in the plots that I'll show you, but you can see other examples in the paper, we used 1 week. If it is less than the novelty regime, then the increment is directly copied from the data, and otherwise every single user is independently following the rules that I stated. Okay, so the total number of installations in each hour will exactly match the data, because that's imposed. And the history window has to be reproduced exactly because, again, that's imposed. One example of a weighting function is just to use an exponential. It's well behaved. And if you use some other ones, and I have written down the names of the formulas of other ones that I use later on, we get qualitatively very similar results. But in general, you could measure it. So it's the response time distribution. Okay, and then T, you can argue about, so when I mentioned 2 or 3 parameters, the total number of parameters would end up having to do with how you actually define this weighting function, right? 1 parameter is just choosing cumulative versus recent, and then you have to worry about H, and then potentially you have a parameter within the weighting function. Okay, so let's suppose you do this. Let me first look at the one on the right. The right is the final distribution, which if you do this from this is actually long time rather than t goes to infinity technically because our time window is finite, but this is a sort of t goes to infinity. And one of the things that you'll notice, so the black stuff is the data, right? So that is whatever it is. But the red, the blue, and the pink, especially the blue versus the pink, all look kind of the same, right? The red's a little bit different, but even that's pretty similar. They all look kind of the same, right? So, yeah.
The red one only has the preferential attachment.
That's right.
Why it doesn't look like? Oh, because they have different.
This is cumulative. Yeah.
Okay.
The red one is exactly right. So the red one is linear preferential attachment on its own, which looks like it's doing an okay job if I take long t. Okay, so you get the long time behavior right for a large region parameter space. But if you look at the time-dependent dynamics, you'll notice that they are totally different. So there are a bunch of papers out there that say, here is some mechanism, possibly preferential attachment. Here's the long-time dynamics. I match the statistics well. Oh, this is my model. That's crap. No, you can't do that. All you can do is say that what you found is consistent with that model, which is why I've only compared a family of 2 models here. There could be some other model that I haven't thought of that I didn't compare that could do better. Who knows, right? Or so you can, and it's useful to do this, right? You have to rule things out. But the long-time dynamics are essentially the same, and if I want to, I can still, say, okay, I can see little differences there. But these 2, right? You would count those 2 as the same for sure. Okay, so the top one is linear preferential attachment. The second one is that I do a recent rule, but with a short memory, which is 5 time units in that case. You may not be able to read this from here. And so this is gamma equals 1. This is gamma equals 0 with t equals 5 and 1 week of imposing data. This is gamma equals 0 with, again, 1 week of imposing data, but now t equals 50. Okay, so these 3 are actually qualitatively different. But the extremes of our model, not even 2 that are slightly different, collapse onto almost the same thing if I only consider long-time dynamics. Okay, you might have data that you don't have the temporal dynamics, then okay. But remember, you can only rule things out. All right, So different dynamics can give apparently something that looks kind of the same, or almost exactly the same, for a long time. Right. Okay, another thing that you could look at, so I think for the next couple of slides I'm not going to go so much, just because probably you guys want to go to the pub. I started a little bit early, it's Friday afternoon, and also because you do more justice just by looking at it in the paper and spending proper time on it anyway. But one thing that can happen, you want individual applications just by random chance to be able to overtake each other and to not have a mechanism that forces the older ones to automatically be first, right? So you want to have a chance of things to happen. So you can take a look at the data and you'll notice that some things definitely do change order. If you take the cumulative rule only, well, it can change order, 4 and 5 do, but you probably know that linear preferential attachment, which admittedly is a crude cumulative rule, you can make more sophisticated ones, isn't the best at having the order change. That's rather well known. There's well documented studies of that. But then you can have a lot more changes in that. So qualitatively, it's nice that this can do that. So this is not a quantitative statement of saying it's right, but qualitatively, it's nice that this rule naturally allows that to occur. Then in terms of the memory range versus history, because one thing you have to worry about is that this this window, we're putting the exact data in there, right? And we only have 6 weeks after that. I'm not really comfortable with saying I put 1 week of data in there and I get 6 weeks out. I would really want the ratio to be much less than 1 week and much more than 7. So that's an area where improving the model would be good. And as I said, Gleason and Moreno and company have done even more mathematical things in papers beyond this. Okay, but so what we did is we just did a fitting. These are rather exhaustive plots that computationally took quite a bit of time on supercomputers at University of Limerick. This is why this Irish Center for High-End Computing thing is on there. And this was just fixing everything except for gamma and h. So now we're saying what's the best gamma, what's the best h in terms of some measure of error. We chose to use the L2 norm as the error in R of A. And so this was just saying which ones were the best. And the type of thing that we were trying to look at was getting the oscillations right. Okay? So given that these all are getting the right long-time behavior, which ones, based on fitting, are getting the right short one? So that's why this is a mixture of doing the simple models and doing the data. So it's a small data project. Yeah.
So why is it so important to have these oscillations there?
Because people have day-night cycles, and that's what people do in real life.
Yeah, of course, but
that's what people do in real life. So we should. That's what people do in real life. So I want day-night cycles in my model because that's what people do in real life. You could change your question and say I want to ask about the trend.
Exactly.
Yes, you could do that. That's a different question.
All right.
People have day-night cycles in real life, so we decided to have day-night cycles in the way we did this. I mean, that's part of human dynamics, right? But yes, for the trend, you don't need that. But then you're specifically asking about the trend and not about the same question we asked. Okay, so I showed you that. You can also ask, do heterogeneous fitnesses help? So in this case, they don't, but of course, there's every reason to believe that something else you study, they could. Yeah?
So the previous slide is fits.
This is fitting.
A single case, a single app.
I don't think so. I think it was fitting to more. I think it was fitting to quite a few.
So you come up with a gamma for the whole system.
So what we do is to say we have only these 2 models we're thinking of. We want to figure out what the best gamma should be, and we want to figure out, we only picked 1 number for the whole system, the way we did this.
But don't you think some apps might be more?
Oh, absolutely. But we want to model with a small number of parameters. Yeah, if I have a huge number of parameters, of course it's going to be that, absolutely. Although, wait till you see what I show you later.
Yeah, but gamma is also the selection of how you choose an app. So the app itself, it's more of a person.
But we're saying all people have the same gamma.
Okay. Yeah.
Which should not be true in real life.
Yeah.
But we wanted a model with a small number of parameters. That was on purpose. But I mean, there are quite a few things that we're assuming that are not true. It is, I think it would not be reasonable to actually think that every person would have the same gamma, even if those are the only 2 dynamics that they could have. But this is just, so it's also a matter of what is this model able to explain? Not is this model correct, because it's not correct. It's what is this model able to explain?
Right. And then the previous slide, when you showed this single case.
This one.
This one. Well, it's a single app, right?
This one on the left is a Yeah, I think on the left is a single app.
Right. And
But on the right it's oh, I see. Yeah, yeah. Sorry, this is a single app. This is an example. The plot's a single app. This one.
right. So and it might be hand-picked, right? Because it looks perfectly fitted.
It is. Well, okay. This is the one that we showed. The general trend of this, and this is. I mean, I don't know, or every, or almost every.
Okay.
It is reasonable to say that this is typical. It is genuinely reasonable to say that it's typical. So yes, a skeptical person can cherry pick. That's not the way I do things, but
No.
but I don't mind. No, that's fair enough. But no, this is actually genuinely. I mean, others may not look quite this good, may look slightly different, but the general point of this, and this one working out the best, that will hold for. I guess I'll say almost all because I don't want to promise that there isn't one that does something strange. Okay, now let me try to go forward in slide space. Okay, so you can ask about heterogeneous fitnesses because in a given situation, you could I mean, in certain situations, you probably need heterogeneous fitnesses to reasonably explain the data. In this one, you happen not to. In fact, for some reason, we actually do worse. I don't understand really, in some deep sense, why we do worse. I understand why we don't do better. And so in any event, whether or not you need heterogeneous fitnesses, and we did a sort of Bianconi-Barabashi form of this, if I remember correctly. Whether or not you need heterogeneous fitnesses just depends on your application. And I think it's really interesting, especially if you're doing OII type of stuff, in which situations do homogeneous fitnesses predict the observed dynamics well, in which do they not? And so it's more of how much of the variation can I explain without putting in fitnesses. I think is a very interesting question on various things. So one example that one might want to do, and I don't have the data of this is with mobile phones, but this is in purchasing mobile phones. What you would have here, suppose you're going from generation N to generation N plus 1, right? The new iPhone 25 comes out. When you go to the next generation, because people will typically tend to do that eventually, you can choose, do I go to the next generation in my brand, or since I'm buying a new one anyway, do I now switch brands? And you can ask questions about whether there are fitnesses that really matter in that kind of question. It's not exactly the same as this, but I'm arguing that some of the things that we think about could be relevant when thinking about a model for that, right? So it's not exactly the same, but just some of the ideas could be useful. Okay, so we were asked by referees, this always happens, of course. We were asked by referees, there was this paper that came out, and I'll show the next plot in a second, but I want to tell the story a little bit first. To look at this paper that came out in, I think it was either Science or Nature, by Wang, Song, and Barabashi, and it was a preferential attachment-based paper, but for paper citations, right, for a different application. But if you're in a fancy journal, and this sort of corresponds to the limit of, let's do cumulative, but let's now make it much more sophisticated and not just do linear preferential attachment. Maybe the reason the cumulative was bad for us was because we did a very unsophisticated one. Okay, fair enough. Now their paper was not designed for this application, right? So, fine. Okay, so we were asked to do that. So, okay, fine. The referees want us to consider another model. Consider another model. We actually did consider several others that I haven't presented. Their model, if you look closely in the paper, you will find that there are 3 free parameters for every node. This is swept underneath the rug a bit in the paper, but if you look really closely, you will find that's true, which means that for us, in that model, we would have over 8,000 parameters. That does not do as well as the model that I showed you, unless maybe there's some corner of parameter space that we happen not to find. So the cumulative perspective, preferential attachment on its own, is just not the correct thing of what's going on here. So there are things that are not preferential attachment, which for me doesn't surprise me, but it's useful to remind people of this on occasion. But it's literally true that with 8,000 parameters versus our 2 or 3, depending on the particular choice of memory window, the 2 or 3 does better because there are other processes going on. Let's see. Okay, I'm conscious of time, but you can look a little bit more at what happens to the turnover plots. The Wang et al. Model has trouble with turnovers of applications, but that's really because even in its sophisticated form, cumulative advantage, if you don't start putting in some other things, is not the best at turnover just because of how it's constructed. And then near critical branching processes. How much of this do I want to explain? Okay, so let's suppose you start from single seed installation, but with no history, and then with equal fitnesses. then you can prove, and I mean prove in the mathematical sense, that the gamma that might be a sign there, that the gamma equals 0 will produce a power law distribution of app sizes with an exponent 3/2, and then asymptotically it will be true in the t goes to infinity limit. In terms of data, it will be true in the long time limit. And it was this observation of a power law that looked like 3/2 in the Onella and Reed Sohas paper that gave James Gleason the suggestion of, oh, maybe these models that are some appropriate modification of what Bentley is doing might be right. Okay, so actually this project kind of started with that discussion, and first checking is that the actual exponent in some reasonable statistical test, and then asking ourselves, is there a reasonable mathematical model that's plausible that could produce that? Okay, so you can prove it for general memory functions. So the cool thing is, with a fairly broad choice of W, you actually get this. This is a general property of things like power laws, that you have variants of the central limit theorem that they can come out very robustly with lots of choices of the components. This is also something that has led to sometimes them being overinterpreted, because there are very generic ways that they can come in from very different mechanisms. Okay, so in any event, you can, in this particular limiting case, you can get that here. The term near critical, just to give you a little bit of intuition for that, that basically means what is the expected number of children for all future times, and if you calculate that and it turns out to be 1, then it's known as a critical branching process, right? So that's what that means. So you can do this over this. You do this calculation with the W, and if your expected number of children is the same as U, then you have that. Okay, so this is something that we do in the supplementary information, which was a cool part in terms of the model working out, but it is slightly a separate story from the how do you model complex systems part. All right, and you can look in the paper if you're interested in that to see that properly. Right. So PowerPoint gave new animations in recent versions, so I like that one because it's symbolic. Okay, so I have 2 pages of conclusions, and then I'll quit. So there's a novelty regime for apps that are younger than about 1 week, and that was basically just kind of looking at the data and saying, okay, it looks kind of, okay, locally it looks exponential. I can't tell you it's exactly exponential, and then it looks linear, right? So I'm purposely being cautious about how I phrase it, but I'm not worrying so much about exactly what the dynamics are, but you can notice a change. It's a clear change. So someone should probably do a change point detection type of calculation to make sure that properly occurs that way. We just did it kind of visually, and in fact there might be some change point calculations in the Onella Reed Sohas paper. After the novelty has worn off, notice the precise phrasing, a model with recent information, which is gamma equals 0, and long memory, which I should have given you these units earlier. This means a mean response time of about 2 days, was what the result that we found from the fitting came in. And equal app fitnesses reproduces the main time-dependent statistical characteristics, right? The recent information model still does well using other response time distributions, so it's not sensitive to the exact function we chose. So in particular, if you use log normal gamma and uniform, you also get very similar results. The nice thing about this is that because we don't know what it is in real life, I don't want these results just falling apart if it's some functional form other than the one that I did, right? That's important. In our case, heterogeneous app fitnesses does not prove our results, but of course there are many situations in which I would expect this to be absolutely crucial. So this is part of a question that one should be asking doing things like this with other situations. And then the interpretation of random copying as a near critical branching process. This will actually, this is what we believe is a good explanation of why we would see heavy tail distributions in this case. I mean, this is subject to the models that we put in, of course, but we believe that this is a reasonable thing in this case. And then in terms of going to the future, because if all we did was talk about Facebook in 2007, there's no reason anyone should care. Maybe similar models for other multiple choice decisions is where I would like to see things like this occurring in the future. And as I said, where James Gleason, Yamir Moreno, and their co-authors have been taking this is to think of you have Twitter and you have a feed and you have things in your queue and you scroll down and which ones do you actually tweet. So they have a couple papers in that particular context that follows on and does more theory beyond what's in this paper. Okay, page 2 of conclusions. All right, so a general note about modeling complex systems, because this is kind of how we had started that project and what we wanted to illustrate by example, what we thought was a good way to do it. many members of our family of models will successfully explain the long-time behavior. And we needed to use temporal information to distinguish them from each other, right? Now, in other situations, maybe it won't be temporal information. Maybe it'll be other information you have, right? But so you have to work, you can always say, I have this fit, it's good. Okay, great. And let's, assuming you do the statistics right, it means you can't rule it out. That's good first step. But unless you have something else, right? Like if you do something in physics, if you do forces, you have Newton's law. You have belief that Newton's law works. So not being able to rule out plus knowledge of Newton's law is something. In most complex systems, in complex social systems, you don't have equations that are as trustworthy as Newton's laws, so you have to worry. Okay, so be careful about drawing conclusions about mechanisms based on long-time behavior. It's useful to study them, they limit possibilities, but you also have to reproduce the temporal dynamics. And if you look in the literature, even now in 2016, there are a lot of erroneous claims in papers. In papers with nice calculations. I genuinely like the calculations in these papers. But then they make these jumps in the conclusions, which I don't think they're justified to make. All right, so thank you very much.